Okay. Okay. So this is lecture 10 of our semester. So let's switch the gears and go to the 2D and multidimensional simulations. So today's lecture is intended quite short. So today we will talk about unstructured mesh for 2D or 3D structures. So I assume that all of you guys already have done some simulations of nonlinear Poisson equations for 1D case. So 1D case, it was not that difficult to solve the nonlinear Poisson equation, but point is now we have to extend our previous treatment for 1D problem to 2D or 3D. Also, the most important one of the most important one in this case is treatment of 2D or 3D case, because I'm afraid that actually well, what is this? My pencil. Where do I have a pencil here and there? Okay, so let me just restart. It's okay. Sorry about that. But okay, so now I can see my pencil. And point is, if we go to 2D or 3D case, one of the most important one is its shape. So shape means that previously when we consider one-dimensional structure, the structure we can consider is particularly this way. Here we have a substrate contact, and here we have a gate contact, and this is separated by oxide, and here we have a silicon. This structure is corresponding to our previous planar MOSFET structure, or other structure we can consider using 1D structure is something like this. Here we have an oxide, and here we have another oxide, and here we have a top gate, and here we have a bottom gate, and it is sandwiched, and this silicon is sandwiched by these two oxide layers. This is corresponding to our double gate MOS structure, and our previous FinFET can be approximated as a double gate. Also, even now our nanosheet MOSFET can be well approximated as double gate MOSFET if the width is quite wide. However, that is just approximation, and if we go to 3D or 2D case, then we can introduce many different realistic shapes. For example, the typical nanosheet just looks like this. So rectangular, like silicon, and that is surrounded by insulating layer. Of course, this is highly idealized one, and in real case, maybe we have a little bit rounded corners and a little bit more thicker central layer. Maybe this elliptical shape will be the same one. Of course, depending on this shape, the difference of device performance will occur. So it can be just a range of percent, not 10% to 20%, but it can be sometimes it can be just a range of 1-digit percent. But in the case of this semiconductor device technology, actually to us 1% difference is quite a big deal. So we never forget about the percent 1% is quite important to us. So in this sense, we have to remember that this kind of simulation or this kind of application is quite sensitive to the change in the range of a few percent. So accurate description of geometry is quite important. So people sometimes say it this way. Okay, this is our nanosheet, and this is cross section, and this is width of our nanosheet. And of course, here we have the third direction, which is not shown in this two-dimensional case. This is channel direction. And when we consider this thickness of our nanosheet, usually this T value is around 5 nanometer or sometimes 4 nanometer. And how large is it? This width, this is orders of several 10 nanometer. So aspect ratio is quite high in this horizontal sense. So sometimes people say that okay, this structure can be well approximated as just the central part here. This can be regarded as double gate MOSFET. Yes, that's true. But point is, here we have a certain part, and this part really makes some changes in our device characteristics. So this is more highly covered by our insulator layer, and usually we know that the inversion of our carriers occur first from this corner side, not in this central side. So accurate description of this two-dimensional structure is quite important. So simply speaking, although we can do many good job with 1D description, but it is true that the description of a two-dimensional or three-dimensional structure is really mandatory. So we cannot avoid the discussion about this multi-dimensional structure problem. So in order to consider this multi-dimensional problem, 2D or 3D, so what we can do is, the first thing we can do is so-called structured meshing. So in this structured mesh approach, we just consider directional meshes. So X directional mesh, Y directional mesh, and Z directional mesh. Three different meshes are separately generated. For example, let's consider this two-dimensional example. Here we have X direction, and here we have Y direction. In this case, we have introduced X directional mesh. So this is the starting point, and here we have another point, and another point, another point. Yes, this is just one-dimensional, but they can be, for example, in general, non-uniformly spaced. Okay. Between these and these points, we have a wider spacing, and here we have a relatively narrow spacing. So we have some freedom to select those points. Another one is y-directional one. In this y-directional one, also we can introduce wider spacing and narrow spacing. So this is up to us. But anyway, point is, now we have built two different meshes, X direction and Y direction, and points of discretized meshes are just obtained by lattice point of these two or three directional meshes. Okay, so means that here we have points, here we have points. So if we have any arbitrary point here, then we can label it with certain two different integer indices. For example, from x directional 1, this will be 0, 1, 2, 3, 4, 5, 6. So its x directional index would be just 6. And how about y directional index? 0, 1, 2, 3, 4. So we will say that okay, its y directional index is just 4. If we use this 6, 4, a pair for describing a certain point without much ambiguity, we can identify the position here. So let me just ask you this question. Where can you find I equals 7 and j equal to 5? Can you pick the point up? Okay, you can do it quite easily because that will be corresponding to this point. So quite similar way, following this quite a similar way, we can identify any point by just using 2 indices or 3 indices if we adopt this approach called as structured mesh. So the mesh is now structured. Okay, this is called structured mesh. This is quite a simple and a straightforward extension of our previous approach to the multi-dimensional cases. Good. However, unfortunately, it is sometimes very inefficient. So consider a PN junction shown in this left side. So this color map shows just log 10 over our doping density. Of course, this relatively red part, can you see the red color clearly? Well, so I think that, well, anyway, this is relatively red and this is relatively blue, and this part more yellow or red part is corresponding to high doping density, and yes, this blue part is corresponding to relatively low doping, or sometimes so that can be regarded as n-type reason, and this can be regarded as p-type reason. So if we adopt this kind of description, then how can we introduce a certain mesh to describe this system? Where is the most important range or reason we have to introduce quite a dense mesh point? Of course, you can now understand here we have significant change of our doping density. So if doping density is abruptly changed in this point, then we need more discretized point to make a fine resolution about the physical quantities. So what we can do is, since this is a PN junction, so maybe we need dense grid along this vertical direction. So maybe you can introduce certain densely populated points here and there. Yes, so sort of a poor drawing, but you know what I mean. Yes, and relatively, if we go to deep inside here, then it is no longer the case. The physical quantities does not change quite rapidly, so you are allowed to introduce a relatively coarse gridding. So that will be a one-dimensional approach. Good. But point is, this system is no longer just a one-dimensional one, and here you can see that also here and there physical quantities, the doping density changes quite rapidly also in this lateral direction. So it means that you need to also introduce a relatively fine mesh in this point and relatively fine mesh for this point. Good. by introducing this x directional or y directional densely populated region, then now you can get quite a good resolution about your physical quantities, but that is related with inefficiency. So think about this one. This is densely populated and this is densely populated. Then what will happen? So it means that the part corresponding to, for example, this part will be well described. Also this part will be well described. Good. And how about this part? Yes, since one of our vertical direction is densely populated, so here we have high resolution. But do we need really high resolution for this point away from this two-dimensional PN junction? Actually, we don't. And please think about this point. Since we have introduced fine mesh along this horizontal direction, also in this shaded part will be highly resolved. However, this is far away from our PN junction. Actually, we don't have to spend more point for this point. Why do we have this kind of inefficiency? It is because we have assigned our points just following these lattice points of each direction. So if any of our directional mesh has a densely populated region, then for certain direction we have more points, although that is not necessary to our device under simulation. So now you can understand well, sometimes it can be a little bit inefficient, and if we go to this right figure, that shows quite much problems of this structural mesh. For example, here you can see that this is corresponding to spacer, and also this is spacer, and they have used also structured mesh, and actually the spacer just looks like this. This is quite much rounded shape. So in order to describe this rounded shape, what they did was, please have a look at this part. Can you see it clearly? In order to represent this rounded corner, what they do is just introduce fine resolution and make some certain discretized version of this one. So in order to describe the smooth transition or not straight line, so we need fine resolution about this system. So also you can see that, you can quite clearly see that this part is finely resolved. However, it is also related with the inefficiency shown here. Of course, this part is really corresponding to our channel region along that direction. So it is really important to get a high resolution. However, this part and this part is away from this channel region and not that important for our electronic transport. But since this is obtained from structured mesh, we have to spend quite a lot of points along that direction. So that's the problem of our structured mesh. Then what is the advantage of our structured mesh? Of course, this is quite easy to consider this structured mesh. Indexing is quite easy, although we have quite complicated three-dimensional structure, but a triplet I, J, K. These three numbers are just sufficient to pointing out a point inside our system. It is quite much attractive, but instead of this efficiency or easiness of your implementation, and the side effect is the inefficiency of your mesh structure. So there is a pros and cons. Yes, that is the situation. So frankly speaking, nowadays in realistic case, nobody is currently using the structured mesh. So the real program is always relying on so-called the unstructured mesh. Here un means that now points are no longer obtained from a lattice point, cross point of three different directional meshes. You are free to introduce any point inside your system, so there is no rule. So although you don't have any rule, but it is your responsibility to have proper mesh structure. If you have just structured mesh, then it is certain that if you have a rectangular structure or rectangular domain, and if you just adopt this structural mesh, then this is quite easy. You can always apply certain numbers, and it is guaranteed that your entire system or entire domain is fully well covered by your points. Yes, but now think about the counter example. Yes, here we have once again a structural or rectangular domain. We wanted to describe this domain with unstructured mesh. So let me just do it in a long way. So what I wanted to do is, yes, I introduced 4 points, and here I have introduced another point. Yes, I have introduced 5 points, but point is just specifying these 5 points is not sufficient to fully describe or fully cover the domain. I mean that instead of considering this one, let's say that now we have 5 points only. Then please imagine the domain out of these 5 points. What will be the domain we can have out of these 5 points? Of course, since we are working with this rectangular one, the first one we can say is that rectangular one. However, let me just give you a counter example. For example, if we say that, okay, this is just a discretization of this system. This V like domain is discretized with 5 points. If I say so, can you make any counter argument against me? Because this is really up to us. Specifying any points inside the domain is not that sufficient to fully cover our domain itself. In order to say this is really for rectangular domain, then actually we must cover our entire domain with basic shapes. So in this case, triangles. So now you can understand In this unstructured mesh, first of all, we have to specify points. So these points are called vertices, and specifying vertices, that is not that sufficient. To us, actually, we have to also specify the triangles or sometimes tetrahedral for three-dimensional cases. So we must specify those basic shapes to build or to describe our simulation domain. So triangles easy to be visualized, and also in the case of a tetrahedron, this is a tetrahedron and this is a three-dimensional shape, and we have four different points, and specifying four different points we can uniquely determine this tetrahedron. So volume can be just obtained from, so three-dimensional domain can be decomposed into several tetrahedra. So this one just shows one example of that domain decomposition. For example, this is a three-dimensional structure, and here you can see that there are many small shapes. Actually, they just looks like triangles. However, actually they are a part of or surface of one surface of each tetrahedron, because this is just a set of attached tetrahedra. So now we are looking at only one surface transparent to us. For example, let's say that here you can see a certain triangle, but a tetrahedron is hidden behind it. So you can see that three-dimensional structure can be decomposed into small tetrahedra. Of course, you can ask me this question. We have talked about basic shapes like triangles and tetrahedra. Is there any alternatives to this one? Yes, of course, we have several alternatives. For example, instead of these triangles, we can also consider a rectangle as a basic building block of our discretization. Also, sometimes we can introduce a more general shape for describing our two-dimensional structure. Also, in the case of this three-dimensional structure, maybe tetrahedra seems to be okay, perfect, but sometimes they can also try to use this kind of shape. Yes, so by using this shape, so this is just a triangle, but here we have just a homogeneity along third direction. So using this one called as a prism, so we can also build three-dimensional structure. Prism was actually quite widely used in our codes in the community, because in the historical development, first people used just two-dimensional structure, and later they were forced to extend their code into three-dimensional one. Also, considering the full three-dimensional one was quite difficult, so as a quick remedy, so they just introduced prism elements into their shape. Then they can easily make just a two-dimensional mesh structure and extrude it to the third direction. Then they were able to generate quite a good mesh quality for simple 3D case. But nowadays the structure is no longer simple anymore. So prism is not that appropriate for our discretization, domain discretization. So now you can understand, okay, in a practical sense, we must use unstructured mesh. So simply speaking, unstructured mesh means that the domain is decomposed with triangles, or domain is decomposed into tetrahedrons. So that is unstructured mesh. And actually introducing a set of triangles or a set of tetrahedra, that is quite a difficult job. For example, well, let me just come back to our previous example. If we have this kind of simple enough structure, then maybe it is not that difficult to make certain triangular grid. Okay, so I can do it. Yes, you can do it. I have introduced 4 different triangles to completely cover this domain. Well, it was not that difficult. However, now think about this funny shape. If we have this funny shape, then how can we make triangles to entirely cover this shape? So also we can define many different shapes like this. Then how can we make triangles? So this is related with a problem called as mesh generation. For a given boundary of our interested region, then how can we introduce a set of triangles or a set of tetrahedrons completely covering the simulation domain? That is really a big problem. Not only interested within this computational microelectronics, every kind of a computer simulation or even animation, they are much interested with this mesh generation. Sometimes if we are working with a certain surface animation, then sometimes we are interested with just surface mesh. Or sometimes, just like us, if we are interested in internal physics, so volume quantities are of interest, then we must introduce volume mesh. The internal domain should be also discretized. So here we have some special programs called as mesh generators, and these programs can generate meshes from the boundary shapes. So for example, let me just give you one example. This is taken from a certain mesh generator. Its name is a triangle. The software name is a triangle, and it means that here we have a quite complicated shape. This is corresponding to a shape of a quite big lake in USA. And now how can we introduce certain triangles by using this program? From this boundary shape, it can generate several triangles, a set of triangles completely covering our domain. You can see that there are many triangles. Then if we ask this program, how did you introduce those points? What is the rule for you placing those points? Then it will say that, okay, I have a rule following this algorithm. So following that algorithm, I have introduced those points. So you can see that surface region, usually what we do is surface region is well described or well resolved, and in this body part, relatively a coarse grid is introduced. this is quite similar to our case. How about our requirement for mesh point? If we have certain silicon here as a channel, then what we have to do is here we need fine resolution for this surface region and relatively coarse graining for this center part if this silicon nanosheet is quite large. However, I wanted to make some warning to our students. So nowadays the thickness is just 4 nanometer, and it is nowadays meaningless to separate the interface and bulk. So the distance is just 2 nanometer or 2.5 nanometer from this interface to the deepest point in this structure. So can you say that 2 nanometer is far away from the interface and we don't have to care about it? So no, actually nowadays, since we have seen so much linearized structures, so nowadays the entire system should be, so at least the channel region should be discretized quite reasonably. Otherwise, you will have quite poor result for your discretized solution. Okay. So anyway, but previously when we consider, for example, planar MOSFET, then of course many MOS devices are surface channel devices, and electrons and holes are found just beneath of a silicon dioxide interface layer. So we were allowed to introduce fine resolution in the interface point and relatively relaxed condition for our nodes in the bulk case. So of course it is our responsibility to generate good enough quality mesh. These mesh generators are just software programs to give us certain candidate for mesh structure. Whether we accept it and use it for our later use, or discard it and try to generate a more discretized version of a given structure, it is our responsibility. So please be careful about this mesh generation. But we will not talk about the topic of how can we generate meshes. This is a really highly specialized field, and we are not experts on this topic. So we will just leave it to the specialist, and we will assume that by some means we have already well described meshes for our interested structure. Okay, so now let's go to how can we treat this already generated structure file. Okay, do you have any question? And let's pause a little bit and waiting for our students' question to me. So do you have any question up to now? In the first part of our today's lecture, I have introduced the difference between structured mesh and unstructured meshes for 2D or 3-dimensional cases. So of course implementation is quite easier for structured mesh. However, so for practical cases we have to use unstructured mesh. So in this semester, sometimes I will just use quite a simple structured mesh to make our life easier, but please don't be confused with this educational purpose course and real world life. In real world, always we must use the unstructured mesh, and sometimes when I use a structured mesh, it is only for easiness of implementation. Okay. Okay, then if you don't have any question, then let me just go to the second part of our today's lecture. Well, then, is there any standard file format for describing three-dimensional or two-dimensional semiconductor device structure? Unfortunately, the answer is no. Of course, we have many different software programs for describing the three-dimensional semiconductor device, and many of them are related with IP, intellectual properties of those companies. Usually they do not open the file to us because just communicating inside their own simulation framework. So it is difficult to discuss the standard file format for universally adopted file format for describing three-dimensional structure. So instead of talking about the standard model, it is my regret if our communities can generate such kind of thing. That will be quite good. But this is really related with a huge amount of money. So instead of that, I have made quite a simple file structure used in this course. So I'm not saying that this is universally accepted to anybody. This is just for our educational purpose. Let's think about this way with an example for a register. So first of all, we have to introduce vertices. So vertices means that points in our 2D or 3-dimensional system. So in this case, I just assume that the structure is 2D. However, if we go to 3D, it is not that difficult. We can just introduce Z coordinates in our vertex file. So when you open a vertex file, then you will see a list of those two numbers. You can see that here you have a certain one floating point number and second floating point number. Each of them is corresponding to either x coordinate or y coordinate in meter scale. So SI unit is assumed here. Then please try to imagine what does it say. It means that here we have 1 micrometer, 1 micrometer. There exists a point. Yes, here we have 1 micrometer and micrometer point is assigned. Please go to the second line. Here we have 0,1 micrometer. So maybe that will be 0,1 micrometer. If you just follow that way, you can identify many different points. So let me just do it together with you. For example, this is corresponding to 1,2. So here we have 1 micrometer, 2 micrometer, and this is corresponding to 0,2. Yes, this is corresponding to 0,2 micrometer. Following that one, here we have 3, and yes, I have covered up to here. After that, we have 1 micrometer, 0. Yes, here we have 1 micrometer, 0, and here we have origin. And finally, we have 2 more points. 0,4. 0,4 is corresponding to here. This is corresponding to 0,4 micrometer, and this is the final point is 1,4 micrometer. 1 micrometer, 4 micrometer. If you just follow this vertex file, then you can identify there exist 10 different vertices, and yes, they are listed in. So can you find any rule for assigning those points? Well, the first one was found. Yes, it was the first one, and it was second one, third, fourth, fifth, sixth. Then I remember that. Well, what was it? It was 7, 8, and 9, 10. That was the appearance of those vertices. Can you find any rule? It is quite difficult to find this. However, also let me just give you one way to describe these points in a more compact way. I mean that x directional, it changes 0 and 1 micrometer, and y directional, it changes from 0, 1 micrometer, 2 micrometer, 3, 4, and make the combination of these 2 by 5 combinations. Then you can easily identify, you can generate 10 different points by a product between 2 and 5. Yes, for this structure, this highly structured case, maybe this is much more, how can I say, efficient way to describe the entire system. However, everybody understands, although it sounds great, but it lacks generality. You cannot describe arbitrary shape with this kind of a structured mesh. So please understand this difference. Well, now you have 10 points, but as I told you before, although we have 10 points, but that does not necessarily mean that we have rectangle here. We must identify also triangles to cover our entire domain. Where can you find that information? For that purpose, we need a separate file. Okay, if we just draw it, then you can identify those 10 points, and that is also described in a different file. I named it as element file, and here you can see this list of 3 different integers. This is not a floating point numbers, but they are integers, and these integers are used to identify index of your vertices. Okay, so here 1 means that the very first point we had. What was the very first point we had in this case? Yes, it was 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. If I remember correctly, that was the appearance order. And when it says that 1, 7, 8, it means that by connecting the first point, 7th point, and 8th point, make a triangle. Can you identify the triangle assigned by this first line? So where can you find the first triangle? One vertex number is 178. Yes, you can identify this triangle is corresponding to 178. Second one is 1, 2, 3, and 1, 2, 3 is corresponding to, yes, this one. 2, 3, 4, 2, 3, 4. Yes, this is corresponding to that way. So by specifying this kind of description, now you can identify many different triangles, and you can also generate a certain um, certain domain. However, I wanted to say this word. Well, it seems quite reasonable, but let me just do it in an alternative way. I assigned this one. I assigned this one. Also, I assigned this one. Also, I assigned this one. Later, I assign this one. I assigned another triangle, and I assigned another triangle here, and finally I assign another triangle. Can you see it? So although we have the same vertices and the domain is also the same, however, you can find that there are multiple ways to introduce our elements, our triangles. So how can we generate those triangles? That really matters to us. Later you will see that sometimes this one shows a little bit worse quality of a numerical analysis compared with the one shown in this one. This one shows much more quite a regular shape of our triangles, and you know that the above one, the above one shows a little bit irregular shape of our triangles, so they can sometimes show different numerical characteristics. Well, anyway, I think that it's okay, and please remember that in this case, in this file format, we are now currently using one-based indexing. Well, if I just do it right now, maybe I will use one-based instead of one-based indexing. I would like to introduce zero-based indexing, but this is not solely invented by myself. So other different formats were just references to generate this kind of file format. So there are many different languages, and many different languages are many different indexing systems. One of them is one-based, and one of them is zero-based, and yes. So unfortunately, in this case, the index is just one-based. So now this is the end of our lecture today, and finally you have homework number 10. You have just 2 days to perform this homework. So please visit our GitHub repository. So when you visit this GitHub repository, so now you can see these 2 files. Can you see it? bjt.vertex and bjt.element. When you click this vertex file, then as I told you before, there are many lines, and each of them is corresponding to the numbers. Oh, here we have 3 different numbers. Oh, is it really 3D? Oh no, this is just 2D, but the third direction is just number 0. It means that although we are showing a triplet, but third one, the z direction coordinate is always 0. Oh, don't be afraid. And as you can see here, you have how many vertex points? The total number is 2,140. So if you try to draw it by your hand or manually placing those points into your drawing program, so that will be quite a disaster. So never don't do that. So instead of that, please write a computer program automatically read this bjt.vertex and bjt.elements. So simply speaking, when we provide just this root name bjt, then automatically read dot vertex file and dot element file and visualize it in this way. So you can identify there are certain triangles and another triangles. In order to do that, what you have to do is first read those vertices and remember it. After that, once you read elements, then by using these elements, draw each triangles. Then you can draw this entire system. Okay, so once you build this kind of a system, so loading structure files, then if I change my mind and change my structure, then of course your code should generate or should visualize this modified structure without much difficulties. So I think that this is a much better way to exchange the information instead of giving all kinds of details to you. But when we have a common format, agreed format between us, when I say a new structure file, then you can immediately start your simulation for this new structure. Okay, so that will be the homework number 10, and please submit your homework before our lecture start in this Thursday. Okay, do you have any question? So if not, then let me just wrap up today's lecture a little bit early, and let me just make a advertisement for our lecture 11. So if you do it successfully, now you have the device structure. Then now you can try to solve a certain partial differential equation on that domain. So in lecture 11, we will try to solve quite a simple equation on a certain given structure. So by using that technique, now you can treat 2D or 3D problem without much difficulty. That is my hope. Okay, so thank you for your attention and see you this Thursday.